All right, let's see here. If I can just not knock my camera off the camera stand, that would be good. It's electrical tape today, see? Because I forgot the thing it screws into, because I made that video yesterday for linear, and then I left the stupid base plate for the thing at home. So annoying. I'll begin with a word of prayer. Heavenly Father, we thank you for this day, and thank you for this class and the opportunity we have just to meet and study your creation. Just help us to understand what we go over today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I just have some final things to finish with chapter 12 on tensors. Hopefully not too long. Famous last words, right? So covariant k-tensors, it means that, what does it mean to be a covariant k-tensor on V-dual? It means that you're looking, I think, at linear transformations on k copies of the vector space back to the reals again. All right, that was his notation. All right, so what we want to talk about is what does it mean for a covariant k-tensor to either be a symmetric tensor or an antisymmetric tensor. That's what we're trying to define. In order to define those carefully, you really need to talk a little bit about group theory. In particular, this is called the symmetric group. The symmetric group is simply the set of permutations on k elements. So that means it's a one-to-one onto map. It's a bijection. When you take abstract algebra, you learn all kinds of stuff about the symmetric group. We don't need all that, but I guess we do need this much. It turns out that any permutation can be written uniquely, well, not uniquely, but it can be written as a product of what are called cycles. And so basically cycles, it's a way of writing the permutation, telling you like which number goes to the next number. And so basically you have for a given permutation, a certain set of numbers will get permuted among themselves, and that makes a cycle. And when you get through studying this, you'll learn that any permutation can be written as a even number of what are called transpositions. A transposition is like just a two-component permutation. So, and it's not unique, but if you rewrite a permutation that can be written by say 8 transpositions, then any other expression of it will have an even number of transpositions. So if you could express it with 4, you could also express it with 10. If you have something that can be written as a product of 3 transpositions, then any other thing will also have an odd number of transpositions. So for that reason, you can define the sign of a permutation is either equal to 1 if sigma is, product of even number of transpositions, and it's -1 if sigma is a product of odd number of transpositions. And this is called a homomorphism because a property of this, for instance, is if you take the sign of, say, sigma 1 times sigma 2, it's actually equal to the sign of sigma 1 times the sign of sigma 2. For example, if you had two odd permutations, right, and you compose them. So the way we multiply permutations is to compose them. That's the group operation, is function composition. So if you compose the two permutations, then that would give you a permutation with an even number of transpositions, because you'd have odd plus odd, which is even. Likewise, down here, you'd get -1 times -1, which would be 1. Okay, so it all works together for good. Great. So I'm not going to get into the details here. I just want to give you kind of just this is a eye in the sky. You'll study this more in abstract algebra, okay? So this is important because this is the nicest way to define a symmetric tensor, all right? So his notation is this. He's sigma acting on alpha of v1 dot vk, all right? it's equal to alpha of V of sigma 1, V of sigma 2, V of sigma k. So what it's doing is it is shuffling it's shuffling the inputs to alpha according to the permutation sigma. All right, it's shuffling the inputs. And from this, he defines the following: sim alpha is 1 over k factorial, sum over sigma in the symmetric group of sigma alpha. And like, to be more explicit, that means sim alpha, if it acts on a k tuple of vectors, well, that's equal to 1 over k factorial, the sum over permutations of k elements of alpha of V of sigma 1. So the symmetrization of a tensor, it simply takes a sum of all possible rearrangements of the entries into the tensor, all right, like it complete reshuffling. And let's see here, and so at the start of this section on page 314, he defines, he says that a tensor is symmetric. So like, let's say alpha, an element of TK V star, is symmetric if, and the way he writes it is like this: alpha of V1 dot 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 VI dot 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 VJ is equal to, oops, my bad, keeps going, is equal to alpha of V1 VJ VI. All right, and that's for all IJ. And by the way, this n sub k that I'm just throwing out as if you know what it means, what do I mean by that?
K, so not through K,
Right, just this thing. Counting numbers up to k, right? So a tensor is symmetric, a covariant k tensor is symmetric if it is if its value is unchanged by any swap of inputs, all right? So he proves on page 314 to 315 that if you take any old tensor, alpha, and you run it through the symmetrization, it produces a symmetric tensor, all right? So like the theorem, proposition 12.14 says this is symmetric, all right? That is symmetric. And also, and more to the point, alpha symmetric if and only if alpha is equal to the symmetrization of alpha. All right? So that's the other part of the theorem. And I would encourage you to look at the proof. It's quite beautiful. It's slick. Even if you don't know group theory, you'll still be able to understand it. Okay? And then, 11.24, I think. 12.14. 12.14. 314 to page 314 to 315 is where that is. All right, next up, he goes on to suppose, all right, so I think the notation that is introduced is that alpha, in this case, alpha is an element of sigma, capital sigma k, of V star. So that's the set of all symmetric K-tensors, all right? And you can prove it's a subspace because the sum of symmetric tensors is symmetric. And you take a scalar multiple, it's symmetric. It's a subspace of the set of all tensors, covariant K-tensors. Next up, he tells us about the symmetric product. Symmetric product. And there we have, let's say, alpha in the symmetric, sigma k of V star, and let's say beta in sigma L of V star. So we've got a symmetric K-tensor and a symmetric L-tensor. And you can put those together, all right? You can put those together and make yourself a brand new symmetric K plus L tensor, all right? And here's the notation for it. Alpha beta is equal to sim of alpha tensor beta. Keep in mind that the tensor product of two tensors has been defined previous in the chapter. We talked about that before. Basically, it's just the obvious thing. You just kind of define it in terms of multilinear maps. If we have the input to alpha has k things and the input to beta has L things, if you feed k plus L things into alpha tensor beta, all you do is just string out the first k things that go into alpha and the second L things that goes into beta, and that is manifestly linear in all the slots and therefore is a multilinear K plus L tensor. So these are K plus L tensors, but then you're symmetrizing those. Now this would be symmetrization done over the symmetric group of order K plus L. All right? And and he has a formula, which I won't write down because it doesn't really, I can write the formula down, but it doesn't really serve anything, okay? What's interesting here, in part, is that I've seen other books use notation here. Maybe some other books might use this notation, alpha circle dot beta, but he doesn't. And I think I realized why. So we'll talk about that towards a little bit later in the lecture, but there's a reason for not, like using juxtaposition for the symmetric product is actually very nice, okay? Because of its application to classical formulas. And anyway, properties of the symmetric product, it's got lots of properties. So like alpha beta is beta alpha. The properties you'll recognize, if I've got, C alpha plus, B beta times gamma, guess what? C alpha gamma plus B beta gamma. All of your favorite, basically, polynomial algebra properties are here. But what's more interesting is that in the case of covectors, what does it look like? In the case of covectors, if alpha and beta are covectors, alpha beta is equal to 1/2 of alpha tensor beta plus beta listen to me, beta tensor alpha. In fact, to be fully honest, that is the place I have more often, the book I was reading, Carton for Beginners by, I forget the authors, but they know who they are. And in Carton for Beginners, that's the notation that's used for that, the symmetric tensor product. So it's symmetrized, right? Like the alpha and the beta, they're playing the same role. It's no respecter of alphas and betas. Yeah.
That's what we used in advanced calculus as notation.
Oh yeah, that's right. That's right. So then next up, we can talk about alternating tensors. And this will not be the last time we talk about alternating tensors, because alternating tensors are exactly where the differential forms live. A differential form is an alternating tensor. All right. And on the tangent space, I believe. So actually, so let me go back and just to save myself a bunch of writing, let's go back here. And let's put a little bracket in here. And let's put parentheses anti. All right. Just add the word anti there. This is going to save me like 3 whole minutes of writing. This is awesome. So anti. Okay. Parentheses. And minus. So antisymmetric tensor is one that if you switch any pair of inputs, you get a minus, what you started with. This is sometimes also called a completely antisymmetric tensor and completely symmetric tensor. That's what I would typically say, because sometimes we have tensors which are symmetric or antisymmetric in just a given pair of indices, but not all. In fact, that's usually the story of differential geometry. You have tensors with mixed symmetry. Some pairs of indices are symmetric, some are not. All right. So basically, if you have alpha in, let's say, T star, oh my bad, what's that thing called? I keep forgetting. TK star of V star and, alpha antisymmetric, then alpha is an element, here's the notation for those guys, lambda k of V star. All right, that is another subspace of the set of all k tensors, k covariant tensors over V star. So you've got the subspace of symmetric tensors, the subspace of antisymmetric tensors. So let's see here. Okay, so we'll talk more about these in chapter 14. We'll come back to this. Like, there is also a complete anti-symmetrization operation, and there's like that part of the story here, but there's no sense in talking about it now because we're not going to use these for the moment. All right, but I will tell you this much, which is that if you have covectors, alpha and beta, right, then the notation here is alpha wedge beta, which is 1/2 alpha tensor beta minus beta tensor alpha. And so like the wedge product is the antisymmetric analog of the symmetric product. We'll talk a lot more about that in chapter 14. Just wanted to mention it today. I think it deserves a mention. It's been mentioned. Okay, great. Also important to mention is that there is a litany of notational identifications given on page 317. You should read it, It's cool. And ultimately, the thing we're probably most interested in is this thing, TKM, which is actually the sections of the covariant tensor bundle of k tensors, k covariant tensors on the dual cotangent, the cotangent bundle. I don't know what the correct way to say this exactly is, but what these things are smooth. They are smooth covariant k-tensor fields. Smooth covariant k-tensor fields. At each point on the manifold, we get a covariant k-tensor. At each point on the manifold, we could either look at the set of symmetric k-covariant tensors or the set of antisymmetric k-covariant tensors. The set of all antisymmetric k-covariant tensor fields on a manifold, those are the differential forms, differential k-forms on the manifold. All right, I'm sure I've talked about those at various points, and the criteria for these being smooth is similar to the ones we've talked about before. If you feed them smooth data and they output smooth functions, then it's a smooth tensor field. Just like if we had a smooth vector field and we fed it smooth functions, if we get a smooth function from that, it's a smooth vector field. Anyway. And again, there's like a C infinity module here in junk. The other thing I wanted to mention here before I go on to the next chapter, which is really where I want to be, well, there's two things I mustn't forget. One thing is, this will help you with the homework, 2 entries are special. Just 2 entries is really special. If we have a bilinear form on V, that would be if I have, like, let's say B is an element of T2 V star, right? In other words, aka B is a mapping from V cross V to the reals, right? We first called it a bilinear form, or a bilinear map, right? Any bilinear map can be decomposed into a sum of a symmetric and antisymmetric tensor. Here's how. So we feed B, let's say inputs x and y, right? And I'll start us out. So 1/2 b of x comma y plus b of y comma x, and then you finish the formula for me. If I want this to be an equality, it's inescapable. Oh, I think I forgot to move the camera back. Sorry, Jeff. Not trying to keep Jeff in the dark here.
Do we do 1/2
Mm-hmm.
bx comma y minus by comma x?
You pretty much have to, right? I mean, if that's the end of the story, that has to be the end of the story. Because 1/2 plus 1/2 is 1, and we're just adding 0. But search your heart and find that this is symmetric, and this is antisymmetric, right? In other words, if I call this thing, b sub 0, and if I call this thing b sub 1, in terms of like the formula, b sub 0 would be an element of what we've called sigma 2 on v star, and b sub 1 would be an element of what we've called lambda 2 on v star. One of your homework problems, which you might find challenging, or you might just find trivial, I'm not sure what's going to happen, because I remember finding it challenging or finding it trivial. I don't remember. I just remember that it was surprising to me. This stops being true for higher rank tensors. So the rank of the tensor is 2. That's an unfortunate term, actually, because other people wouldn't say rank, because rank has a meaning in linear algebra in terms of like the dimension of the subspace of the image of the mapping. And when we talk about the rank of a tensor, it's not like that if I'm saying it here. But it is like that for some people other places. So watch out for rank of tensor. Don't assume, double check on what that means for a given person, okay? Anyway, for a k covariant tensor, k greater than or equal to 3, there is no such decomposition. If you look at, if you just count, you can count the dimension of the symmetric tensors. You can count the dimension of the antisymmetric tensors. You can work out a basis for each of these, all right? And you'll find out that there's not enough things in those bases when you put them together to get the totality of the k covariant. Like the dimension at a point of like, the k covariant tensors is n to the k, all right? So like if I have 3 tensors, like T3V, I've got n cubed is the dimension of it. So if I'm talking about like 3 dimensions, the rank 3 tensors, there's 27. It's a 27-dimensional space. All right, in 3 dimensions, there is just one 3 antisymmetric tensor. It's E1, wedge E2, wedge E3. That is the only up to linear independence 3 form on R3. And the symmetric tensors on R3, all right, are essentially just, goodness gracious, may just be the same. Is that right? Is there just one? Huh. Yeah, maybe there's just one. I'm not sure. I don't know as much about symmetric tensors. I haven't worked a lot with them. But I think that's true. If my intuition isn't, if intuition's not failing me, there is just up to linear independence one symmetric tensor of rank 3 on R3. Oh no, that's wrong. Because I could do like, I have a strong suspicion, for example, I could do E1, E2, E3. But I could also do like E1, E1, E1. I could do E1, E1, E2. You see? You know? But this would be equal to like E2, E1, E1. All right? So it's not like there's not 27 different symmetric rank 3 tensors. There's however many different patterns that aren't related by the commutation relations, you know? Like there's what? E1, E2, E2. Anything else? Obviously you got E2, E2, E2. E3, E3, E3. How about E1, E1, E3? Or E2, E2, E3? Or E3, E3, E2? I don't know. Do I have them all?
E3, 3, 1.
3, 3, 1? I'm missing 3, 3, 1. Cool. Very good. See, if I was better at combinatorics, you'd recognize this as a particular well-known problem in combinatorics, and you would just rattle off the answer for me. That's the dimension of the symmetric 3 tensors. My point to you is that we're not going to get to 26. And since I already know that lambda 3 is one-dimensional, the sum of the symmetric and the antisymmetric 3 tensors is not 27, which means there are tensors of rank 3 which are neither symmetric nor antisymmetric, nor can they be written as a sum of the two. So one of your homework problems is to show that, I think it's E1 tensor E2 tensor E3 is, see, this is not equal to, right? This is not equal to E1 tensor E2 tensor E3, right? Because it's the symmetrization of E1 tensor, E2 tensor, E3, right? But anyway, yeah, so I don't want to blather on too much about that, but there's a homework problem to explore that. The deeper question is, okay, so if their arbitrary K tensor is not just the sum of a symmetric and an antisymmetric tensor, what is it the sum of? That's an interesting question. It leads to the study of what's called representation theory. Representation theory gives an answer to that. It tells you how to decompose a rank K tensor as a sum of what are called irreducible tensors. But this is a difficult problem which requires its own course. It's important to physics though, because the different irreducible tensor representations of these things correspond to different physical states of particles and stuff like that. So anyway, there's that. Now, the other thing I was supposed to tell you guys about was the tensor pullback. So if we have a symmetric K tensor here, and suppose we've got F, a smooth map from M to N, right? And let's say alpha is an element of the K tensors at the cotangent space of n at f of p, then define d f star p of alpha, an element of t k tp star m. So at the moment we're defining the pointwise, the so-called pointwise pullback of alpha by f at p. It's a lot of, say that 3 times fast, you know? I thought you're accepting the challenge. Very nice. Challenge accepted. Very good. All right. So here's the pointwise pullback of alpha by f at p. D f upper star p alpha. It acts on v1 through vk, and it is defined to be alpha of d f p v1 d f p of vk. So basically, to put this into words, the pointwise pullback of a k-covariant tensor at f of p is simply defined by taking that k-tensor and evaluating it at the push forward of the arguments. See, this is the push forward of f at p. So it's the same thing we did in chapter 11 with the pullback of a covector. It's just now instead of having one entry, we have k. Same exact idea though. And if you don't do this at just one point, if you do it, he says we define a rough k-tensor field. So if like, if he says if A is covariant k-tensor field on N, we define f star A at the point P to be df star, the pointwise pullback of P of A at f of P. Yep. And then he gives the formula for how that acts, which is completely unsurprising because it's what we wrote right here. Okay. And he says it's a rough k-tensor field because in principle you could pull back, you could even pull back things that aren't smooth. You notice that at no point are we differentiating, we're not differentiating the covariant k-tensor we're pulling back. All of the differentiation is happening for the manifold map, the f that goes from M to N. So like in principle you can do this even for just a continuous covariant k-tensor field or even a discontinuous one, whatever. Of course, there's a theorem. If A is smooth, then the pullback of A is also smooth, the usual things. And there's also super nice properties for the pullback. Proposition 12.25 tells you some very unsurprising things. So, for instance, the pullback of f times b is f composed with big F times f pullback b. And the pullback of a tensor of A and B, a tensor B, is, guess what? It is the tensor of the pullbacks. And the pullback is additive. And I don't think any of these would be difficult to prove. I may not even put them in your homework though, just because, you know, Here's one, G composed with, this one's a little bit, maybe this is interesting. G composed with F, pull back B is F pullback of the pullback of G, B under G. And finally, the identity on N pullback B is equal to B. So if you, exercise 12.26, prove proposition 12.25. I hope I didn't assign that because it would take me forever to write up that solution. I'm kind of tired. As a comment to corollary 12.28, I say noise. Like corollary 12.28 is amazing. It simply says, basically, to calculate the pullback of a K-tensor field, what you do is you just plug in the formulas for the map. It's the substitution lemma again, just like we were doing in chapter 11. So I won't write it out, I'll let you read it. And that's pretty much it. There's a bit at the end of the chapter about Lie derivatives, but I guess I could try to write the definition and explain it, but I have a bad feeling about doing that today, so I'm not going to. Okay? But there is a couple pages on the Lie derivative of a tensor field. Let me just tell you what it does. I think I've assigned you a homework problem or two which touches on the Lie derivative, so you do need to read about it to do those homework problems. I don't think it's a main character in our course, so I'm hesitant to get too much into it. It is important, the idea of a Lie derivative. So let me just say a couple of words in support of caring about the Lie derivative. First of all, it's got the name Lie in it, so, you know, come on. All right, let's go. Wait a minute, no. There's no going. We can't go today, there's no Jeff. So, anyway, so the Lie derivative of a K-covariant tensor field, which is smooth, is again a K-covariant tensor field. And so you take the Lie derivative of a tensor with respect to a vector field. And what that does is it describes the change of the tensor in the direction of the vector field. That's essentially the meaning. The way the definition is set up is you take the tensor and you flow it along the flow of the vector field. And then you could take a difference quotient comparing the tensor field at the point where it's flowed to versus the point where it started. And so you can calculate essentially a derivative because you can take the difference of, you know, the flowed tensor versus where you started. And that defines a Lie derivative. However, no one actually ever takes that limit because after a technical lemma or two, you learn that there's a beautiful simple formula for the Lie derivative. And so the homework problems I've assigned you guys, you'll be able to solve with the beautiful formulas, which you'll find at the end of chapter 12, which are relatively simple. It does come up again. There's a natural notion of differentiation of differential forms called the exterior derivative. And to understand the exterior derivative, there are certain identities which involve the Lie derivative there. That's the place I would say it comes up most, that I'm most interested in. But what I'm more interested in doing for the remainder of today is talking to you guys about Riemannian geometry, because I want to make sure we get to that today, because that's an actual honest-to-goodness example of a symmetric tensor, which is, you know, kind of important. In fact, the reason that we're here and talking about any of this probably is Riemann. You know, do you guys know who Riemann was? No. So Riemann, I guess, was a 19th century mathematician, and it's one of those few characters, I think, that actually impressed Gauss. And I think that's right. I think he and Gauss are in the same time frame there. And anyway, when Riemann got hired to be a professor at one of these prestigious German universities, I think it was, he had to give a talk And so it was the custom for you to give this talk at the start of your professorship that kind of laid out your grand idea for the research which you were going to do, you know, as that prestigious professor. And so if I understand this correctly, this is what happened. He gave this speech about his vision for, well, what we now call manifolds, right? And essentially he described the concept of an n-dimensional curve space and how you should think about it, and, you know, different existing questions. Of course, people had already been thinking about surfaces and probably some aspects of higher dimensional space before that point, but it really was a grand vision that sent people in different research directions for the next 50 years. Enough so that even though I wouldn't say it was like the main line of mathematics, by the time Einstein came around in the early 20th century, like 1910 or so, there was already a pretty well-developed theory of Riemannian and semi-Riemannian geometry. So like Einstein didn't have to create all of that mathematics. It was there waiting for him to use to write down the theory of gravity and curve space, which ultimately rests on the calculus that we're looking at. So Riemann was sort of the father of a lot of this thinking, but and so that's why it's called Riemannian geometry. But Riemannian geometry specifically is when we have a manifold, and let me just write definition. So a definition, a Riemannian metric is on M is a smooth, symmetric, covariant two-tensor on M that is positive, definite at each point. All right. A Riemannian manifold a Riemannian manifold is a pair M comma G, where M is a manifold, and it can be a manifold with or without boundary. Okay.
Symmetric.
Oh, it says without boundary actually. Let's see here. It says a Riemannian manifold with boundary is defined similarly. All right.
Is it symmetric in the usual sense of metric?
I just defined it right there. Riemannian metric on M is a smooth, symmetric, covariant two-tensor on M that's positive, definite at each point. That's the definition. So a pair, M comma G, where M is a manifold and G is a Riemannian metric. I think to start with, we want to think about manifold without boundary. But if I recall correctly, he does eventually get around to talking about what to do with the boundary. So, but to keep things simple, let's say no boundary for the moment. Well, I guess he says if M is does a Riemannian manifold with boundaries defined similarly.
Riemannian metric down there, and G is Riemannian.
Oh, yes. Good grief. Thank you. Duh. So can you guys tell me what the definition of positive definite is?
It's either never negative or never less than positive. It should be never negative.
Mm-hmm.
It can be zero, I think.
Is it well defined and positive?
Yeah, never negative. So, and I guess if it's 0, it ought to be, well, that's not it. No, I don't know if that's what it is actually. Tell you what, I did not have it. Yeah, look at it. If you're going to Google it for me. Thank you. Sorry guys, I meant to look up a technical definition of that for you guys before. I remember something, but I'm not sure it's the right thing to tell you. So.
Tell me about matrices.
Yep. Okay, go for it. What's it say about matrices?
A symmetric matrix M real entries is positive definite if the real...
Hold on. Symmetric matrix M with real entries. All right.
Is positive definite
All right.
if the real number lowercase z transpose m z is positive for every non-zero real column vector.
For all z not equal to 0. Z and Rn. Okay. Yeah. So let's see here. All right, so trying to stick to the book here as much as I can. All right, so let's talk about it. Now, Ernesto, I know you want to connect to the concept of metric, like in the sense of topology, and we'll get there. All right, that soon happens. It turns out that you can define a metric on the manifold using, in that sense, but we don't call that a metric in here. We'll call that a distance function. The metric will be the symmetric covariant 2 tensor on M that's positive definite at each point. So let's see here. So he says in smooth local coordinates, the Riemannian metric can be written like this: G, and I'm going to put the sum in because, you know, sorry, I just want to put the sum in. So Gij dxi tensor dxj. All right, that would be, for points in the manifold that are covered by the chart X. Okay. And then he says where G is a symmetric positive definite matrix of smooth functions. So that means exactly what we wrote here. All right, but you can imagine instead of having real entries, you have real functions, right? And at each point, if you take a, well, anyway, I mean, I think a way we could write that explicitly would be something like this: G of, like V is greater than 0, right? And you could put a sub P here if you want to say a P, and I could put a sub P here if I wanted to, and a P here if I wanted to here. This is greater than 0 for all VP in TPM, VP not equal to 0, right? And that has to hold not just at one point, but for all points in the manifold. That's positive definite, written at the level of tensors. But what that means is that if we look at the matrix of the form, all right, which we're about to talk about here, what is that noise? It's embarrassing, honestly. Like, it's just embarrassing. But So like the matrix is literally Gij. How do you find that, right? So let's see here. I mean, we could do a bunch of different calculations here. Let's do a few. Let's work it out. So what if I feed this, say, G of VW? What's that look like? So the way that works, right, is we do dxi of v, right, and dxj of w, right? But do you remember how that works? What does it happen? What happens when we let dxi act on the vector v and dxj act on the vector w? It just picks out. Yeah, exactly. Those are the coordinate functions. You know, those are the coordinate maps. Really, these differentials play that role. So anyway, Gij, vi, wj. So you can look at that if you want to, right? You can look at that as being equal to V transpose times the matrix G times W, where G is the matrix Gij. See, we can look at that as a matrix calculation if we want to look at that in coordinates in that way. And so we can talk about the matrix of the form in this way if you wish to. Okay? And that would be a symmetric positive. That would be a positive definite matrix. It would also be symmetric. See, because this is equal to, notice that G of VW is equal to G of WV, right? And so that would tell us what? That would tell us, like, you know, V transpose. Well, let me get to the point here. Let's not be dumb. I'm sorry. I'm being dumb. I don't need to do all that. What is Gij though? Okay, so like Gij is specifically what? It is equal to G of partial xi, right? Comma partial xj, right? Do you see why that's true? What happens when I put partial xj in here? Partial xi rather, and partial, maybe I should use different letters, you know, partial k, partial xl, let's say. That, exactly, those become Kronecker delta, Kronecker delta ik, and Kronecker delta jl. And so the summation over I and j squashes, and I could say this, KL is KL, right? But the tensor is symmetric, right? So we have this, right? Which means we have G, L, K. So a symmetric covariant tensor has symmetric components. And if I was to look at the big matrix G that I was just talking about, it's pretty obvious that that would be a symmetric matrix. G transpose would be equal to G, right? Which means that it is an orthonormally diagonalizable matrix. The real spectral theorem applies. There exists an orthonormal eigenbasis for G. We can choose a system of coordinates at a point which diagonalizes G with the eigenvalues of G down the diagonal. Now, we can't do that necessarily at more than, you know, like, we can't do that globally perhaps. But at one point we could, you know, orthonormally diagonalize it. It's a more subtle question is if you can do that at more than one point at once, you know. All right, so. All right, now that we have this, let's say a little bit more. We can say more. And So this is I was like so impressed with this book and its choice to not use the symmetric tensor notation. And the reason for that, I'm about to show you. It's nothing terribly profound. It's just, I really like this notational choice. So if we got the metric, right, and it's equal to the sum over I and j, right, of gij dxi tensor dxj, right? We can write that anew as follows. See, we can write that as, let's see here, how can I do this? How about this? The sum over I less than j gij dxi tensor dxj plus the sum over I greater than j gij dxi tensor dxj plus the sum over I equals to j. Or if you like, we could just do sum over I, right? GII dxi tensor dxi. So I can say, well, that's really the sum over I less than j of gij dxi tensor dxj plus, let's switch the index. Let's relabel it. Say, you know, I don't know, k greater than L, right? And then we'll have dxk tensor dxl. And I'm just going to call this thing Pac-Man. All right. Now, I would put GKL there, but I want to use the symmetry of G. So I'm going to put G instead of KL, LK, right? Okay. And then notice the pattern. So I have, let's see here, let's rewrite that back in terms of I and j. So I've got the sum over I less than j of gij dxi tensor dxj. And then over here, I'm thinking of, I'm going to relabel L as I and K as J. All right, so we've got, I said relabel L as I and K as J. So then I've got dx, L as I, J as K. So dxj tensor dxi plus Pac-Man. But then I have the sum over I less than j of gij dxi tensor dxj plus dxj tensor dxi. Right? And check this out. No Pac-Man.